Ever pondered how trees and mathematics intersect? It's not about counting leaves or branches, but about a concept called trees in mathematics. This intriguing connection between trees and mathematics might seem unusual at first glance. One might think, what do trees and numbers possibly have in common? The answer lies in the concept of trees in mathematics. Now, we're not talking about the kind of trees you see in a park, but a term used for a particular type of graph in the mathematical world. These mathematical trees are integral to understanding many mathematical problems and provide a solid foundation for numerous computer science issues. They are essentially a way to visualize and understand relationships and connections. They can represent everything from the organization of a company to the connections between web pages. So, trees in mathematics aren't about nature, but about connections and relationships. We'll delve deeper into this fascinating concept in the coming scenes. Stay tuned. Trees in mathematics are a type of graph, a set of points connected by lines. But what makes a graph a tree? Let's dive in. A tree, in the mathematical sense, is a graph, but not just any graph. It's a specific type of graph with two key characteristics. First, it's connected. This means that you can get from any point or node to any other node by following the lines or edges. No node is an island, so to speak. Second, a tree has no cycles. A cycle is a path that starts and ends at the same node without retracing any edge. Imagine you're hiking in a forest following a trail. If you end up back at your starting point without ever doubling back on your path, you've just walked a cycle. But in a tree, that can't happen. Every path you take is a one-way trip from one node to another. Now, let's consider a couple of examples to clarify these points. Picture a star shape, where a central node is connected directly to several outer nodes. But the outer nodes aren't connected to each other. That's a tree. It's connected, since you can get from any node to any other by going through the central node. And it has no cycles, because there's no way to start at a node, follow some edges, and end up back where you started without retracing your steps. On the other hand, imagine a square shape, where 4 nodes are each connected to 2 other nodes, forming a loop. That's not a tree. It's connected, sure, but it has a cycle. You can start at any node, travel around the square, and end up back where you started. So, when you're looking at a graph and wondering if it's a tree, check if it's connected and if it has no cycles. If it meets both criteria, congratulations, you found a tree. Remember, a tree in mathematics is a connected graph with no cycles. If you add one more line or remove one, it's no longer a tree. Now, you might wonder, where do these mathematical trees come into play? One answer is in minimum connector problems. To grasp the concept of minimum connector problems, let's think about a network of cities that need to be connected by roads, or perhaps a set of computers that need to be linked via cables. The challenge here is to design the most efficient, which usually means the shortest network of connections. In mathematical terms, this is known as a minimum connector problem. But how do we solve such a problem? This is where trees come into the picture. Remember, a tree is a type of graph, a network of points connected by lines with no cycles. In our road or cable network, each city or computer is a point, and each road or cable is a line. To find the most efficient network, we need to find a tree within our graph that connects all points while using the shortest total distance, or, in graph terms, the smallest total weight. This is called a minimum spanning tree. By finding this tree, we solve our minimum connector problem. Now let's consider a real-world application. Suppose we're a telecommunications company planning to lay out fiber optic cables to link a set of cities. To minimize costs, we'd prefer to use the least amount of cable, which means finding the shortest possible network of connections. This, in essence, is a minimum connector problem. And how do we solve it? Exactly, by finding a minimum spanning tree within our network of cities. Each city is a point in our graph, and each possible cable connection is a line with a weight equal to its length. By finding the tree that connects all cities while using the shortest total length of cable, we've found the most cost-effective solution to our problem. So, whether you're planning a road network or designing a computer network, The concept of trees in mathematics can come in handy. They provide an efficient solution to minimum connector problems, helping us to design the most efficient and often the most cost-effective networks. In essence, minimum connector problems are about finding the most efficient tree within a graph. This brings us to another important concept, the spanning tree. Now, you might be wondering, what is a spanning tree? Well, in its simplest form, a spanning tree is a tree that connects all vertices of a graph. That's right, every single point or vertex on a graph is connected, but there's a catch. There are no cycles in a spanning tree, much like the trees we've been discussing. So, why is this concept important? Well, spanning trees play a crucial role in solving minimum connector problems. Remember those problems we talked about earlier, like designing the most efficient network of roads or connections? Spanning trees are the secret sauce to solving those problems. Let's imagine for a moment that we're trying to connect several cities with a network of roads. We want to do this in the most efficient way possible, meaning we want to use the least amount of road. In this scenario, the cities are our vertices, and the roads are the edges connecting those vertices. The most efficient network of roads would be a spanning tree, as it would connect all cities without any cycles, ensuring the least amount of road is used. But how do we find this spanning tree? Well, there are several algorithms or step-by-step processes that we can use. Some of these include Prim's algorithm, Kruskal's algorithm, and Boruvka's algorithm. Each of these algorithms uses a different approach, but they all aim to find the spanning tree of a graph. So let's bring it all together. Trees in mathematics are a type of graph, a type of connection. They are connected graphs with no cycles. Minimum connector problems, like designing efficient networks, can be solved using these trees. And a spanning tree, a tree that connects all vertices of a graph, is paramount in solving these problems.